Hello everyone, I'm glad to share my recent research with you here. In this brief presentation, I will talk about our novel confidential and private decentralized learning algorithm, which is named CaPriDe Learning. Our proposed CaPriDe Learning algorithm utilizes fully homomorphic encryption and knowledge distillation concepts to obtain confidential and private decentralized learning algorithm. And we propose an encryption-friendly distillation loss that estimates the approximate KL divergence between model predictions in the encrypted domain. Extensive experiments indicate that our algorithm enables participants to achieve positive calibration gain, even in extreme non-AD settings. Here's the outline of the presentation. Federated learning is a special case of collaborative learning that operates under the coordination of a central server. FL enables multiple entities to collectively address a machine learning problem by sharing specific updates, such as gradients, rather than raw data. This type of FL is referred to as cross-device FL. Cross-silo FL has been widely recognized as a promising solution for addressing the data fragmentation issue in domains such as finance and healthcare. Cross-silo FL typically focuses on preserving the privacy of local data. Existing FL algorithms are vulnerable to gradient reconstruction attacks. What we ideally want is to make cross-silo FL decentralized, where it doesn't rely on central orchestration, therefore mitigating gradient leakage attacks. Instead of sharing gradients, which can be prone to leakage, we exchange distillation losses to address the privacy-utility trade-off efficiently. Knowledge distillation involves transferring knowledge from a large, complex model to a smaller, more efficient model. This process enables the student model to approximate the teacher's performance, often with improved efficiency and faster inference times. As described in this figure, the student model uses two losses: student loss that uses hard predictions to match with the ground truths, and distillation loss that uses its soft predictions to mimic the teacher's predictions. Homomorphic encryption is a cryptographic technique that enables computation on encrypted data without the need for decryption. By preserving data privacy throughout the computation process, it addresses critical concerns associated with data security and confidentiality. As outlined in the figure, the client sends encrypted data to the service provider, and the service provider performs an unencrypted inference on the received data. The computer results are then sent back to the client, who can decrypt the obtained data. This way, only the client can see the data and the results, ensuring privacy and confidentiality. Next, in this figure, we see the schematic representation of how our proposed CaPriDe Learning works, considering PK as the querying party and PL as the answering party. It's important to note that L can take values from 1 to K, denoting the number of clients. The dashed line indicates the secure transmission of information, and the blue color process occurs solely at the beginning of the protocol. Specifically, the parties exchange the encrypted data with each other initially and compute pairwise distillation losses of each other using their own FEG-compatible models. Then, the querying party receives the pairwise distillation loss, decrypts, and uses it to improve its model by performing backpropagation in an unencrypted domain. Here we present the equations, the overall loss of PK, where we employ cross-entropy loss and the distillation loss, the total distillation loss that is used for aggregation, and the pairwise distillation loss. In the case of pairwise distillation loss, FHE domain supports only linear operations. This way, we approximate the KL loss to be encryption-friendly by omitting the log sum exponential component highlighted in red. Although this red component ensures that KL loss values fall within the range of 0 to 1, dropping it doesn't impact the knowledge distillation process. It merely shifts the obtained final values. Following, this table lists the datasets, which include CIFAR-10, CIFAR-100, and HAM-10000. For all our experiments, we employed the ResNet 18 architecture consistently. The baseline models we used are fit averaging with differential privacy, and deep mutual learning. We employed various data partitioning strategies, including homogeneous, heterogeneous, and non-overlapping class distribution. For CIFAR-10, we also present the validation accuracy plots for the specified settings. It's evident that from the plots, fit averaging outperforms other methods in terms of accuracy. However, this improvement in accuracy comes at the expense of privacy, since fit averaging involves sharing and aggregating full model parameters. On the other hand, fit averaging with DP provides a good level of privacy but results in a degradation of utility. Hence, CaPriDe Learning achieves a favorable balance between privacy and utility when compared to standard FL algorithms. Now we present the per class accuracy on the Cypher10 dataset, demonstrating that in all settings there is a positive calibration gain. Additionally, we observed that the class standard deviation of class accuracies is reduced compared to individual training, indicating a smoother performance across different classes. Next, a per participant accuracy plot on Cypher100 can be used to draw a similar conclusion. Furthermore, we compare our proposed approximation of KL loss with the L2 loss, which is compatible with FHE. In our evaluations, CaPriDe Learning with our KL loss outperforms the case with L2 loss. We also provide a report on the FHE configuration parameters and the memory computational requirements for the selected datasets using the ResNet 18 architecture. To conclude, we developed a new collaborative learning algorithm which exploits encrypted inference and knowledge distillation to achieve confidentiality and privacy without any central orchestration and any need for non-private shared data, and an encryption-friendly distillation loss that estimates the approximate KL divergence between model predictions and design a protocol to securely compute the loss in the encrypted domain. Extensive experiments on the benchmark datasets show that CaPriDe Learning achieves better privacy-utility trade-off among the compared methods. You can find our code using this link. That is all. Thanks for listening.